Hello, this is Mr. P, and today we're going to talk about graphs of functions. And we're going to start with the geometric interpretation. We're going to look at what is the geometric interpretation of x and f of x. Looking at the graphs, x is going to be the directed distance from the y-axis. Now, it's a very important word, directed. The directed distance means that it could be positive, it could be negative, it does have a directional component. So for example, since x is a horizontal idea, we think of left and right when we think of x, then along the x-axis, a positive 3 on the x-axis means it's 3 to the right from the origin, and a negative 3 distance in the x component means it's 3 to the left. So to the right is positive, to the left is negative. Now for f of x, which is the same as y, remember, our ordered pair x comma y can also be written as x comma f of x. So the f of x, or in other words y, is the directed distance from the x-axis. So that is either up or down. And it's the way you would think. Up is positive and down is negative. So both of them are directed distance. That means it could be positive or negative or 0. Now we're going to look at example 1 is we want to find the domain and range of a function, and we are given the graph. Starting with the domain, remember that the domain is a left and right idea. So this is the interval that deals with the domain. And we think of x values. When we talk about domain, we are talking about x values, we're talking about left and right ideas. So visually, and you can do this sort of in your mind, if you think of sweeping a vertical line across your graph. And notice that our graph does have a beginning and an end. It doesn't go off to infinity in both directions. But think about sweeping a vertical line across the graph. When you first touch the graph, that will be where your domain begins, because that will be the x value that has a y value on the graph. That is to the left of this. Notice how there is no graph to the left of this vertical line. So therefore, the graph doesn't start, or the function is not defined until we get to at least this point in this value of x, which is -1. So at -1, we have, this is the point where our graph begins, and then as we sweep along to the right, we have a graph until we get to, this is the last point where our graph exists. So our graph only exists between -1, we're talking about x values here, between -1 and +4. So as far as numbers, it's going to be -1, 4 are going to be the endpoints of my domain. But then also notice how for the point where x is -1, that is a filled in circle, which means that point is on the graph. And this is an open circle, which means that point is actually not on the graph. So as far as our interval is concerned, we're going to have a bracket on the left, we're going to have a parenthesis on the right, because it's the interval from -1 to 4, including the left bound, but not including the right bound. Now, I'm going to skip over B for a second. We'll come back to B. Looking at the range, we are now thinking of an up and down idea. So we're going to think of a horizontal line that we're going to move up and down, because the range has to do with this interval here. So instead of left to right, we're going to move down from the bottom to the top. That way we're increasing our range numbers. So this would be the smaller range numbers, and this would be the higher range values. Alright, so starting from the bottom, we come up until we hit the graph. And this would be the beginning of the interval for the range. And remember, range has to do with y values. So from this point, we don't care about the x value, we care about the y value now. So we're going from -5, and then we're going up, 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 past this point, because we have y values that are higher than this point. We keep going up until we get to this point. The graph does not exist above that point, so that would be the upper bound for our range. So again, number-wise, we're going from -5 to +4. Those are the y values. Range has to do with y values. And notice how for both of those, they are both filled in circles. So we are going to have a closed interval from -5 to 4. So it includes both endpoints. Now for the function values, what is f of -1, f of 2? Well, let's start with f of -1. You can think of that as the input-output. If x is -1, what is f of x, or what is y? So you would go to -1 on your x value. That is, your input is your x value. So I'm at this point here, and then I either go up or down until I hit the graph. So here I want to go down to hit the graph, and at this point, this is the y value here is the value of the function at x equals -1. So f of -1 is going to be that y value, which is -5. So when x is -1, y is -5. That's your input, that's your output. So f of 2, for example, says, well, if x is 2, what is y? Well, we go up to here, and we find that y is 4. The order pair 2, 4 means if x is 2, then y is 4. All right, let's look at finding domain and range when you're given the equation. So we have f of x equals the square root of x minus 4. Now, we've done one like this in the past, but we were only finding the domain back then. Now we're going to find the domain and the range. So again, the way to look at this is with the understanding that the radicand, which is the expression underneath the radical sign, must be non-negative. And be careful when you choose your words. We're not saying it must be positive. We're saying it must be non-negative, because it could be 0 or positive. Square root of 0 is still 0. So the radicand, which is x minus 4, therefore must be greater than or equal to 0. That's what non-negative means. Now we're going to solve this. We add 4 to both sides, find that x must be greater than or equal to 4, and then we can figure out our domain from this, because remember, domain is x values. So our domain is going to start at 4, and it's everything to the right of. Greater than on a number line means to the right of. So it's greater than or equal to. So we're going to start with our bracket starts at 4, which means we include 4, and we're going up to infinity. We have the bracket because we have the or equal sign, and remember, the infinity will never have the bracket. It's always going to have the parenthesis. So if we look at the graph of this, if we were to plot, notice how the graph doesn't even exist to the left of 4. It only exists when x is 4 or larger. So if we think of x equals 4 and we put that into our function, 4 minus 4 is 0, square root of 0 is 0. So when x is 4, the value of the function is 0. And then as x gets larger, our points, our graph will increase. So it will be always increasing to the right. And by making the graph, that is the easier way to answer the question of what is the range. It's easiest to just look at the graph. So the domain we can get from this idea, but now we want to look at the graph to figure out the range. Now the range, if we look at, the graph doesn't exist below the x-axis, so thinking from bottom to top, the first place we're going to have any graph is at 0. And then from 0, the graph will go up forever as we go to the right. So our range is going to be from 0 to infinity, again, including the 0, because that point 4, 0 does exist on the graph itself. Remember, 4 is the x value, and 0 is the y value of that first point. All right, so that would be the domain and the range. Now, there is a test for a vertical line test for functions. And it's pretty simple. If you can do it in your mind, mentally you want to think of a vertical line, because that is the vertical line test. And you want to take a graph. This is a cubic graph, or it's at least a cubic polynomial. It could be a higher degree, but it's at least a third degree polynomial. And this is at least a second degree polynomial, or second degree equation. Now here, for the vertical line, we want to think of passing a vertical line and sweeping it across the entire graph. And the question you ask yourself is, does the vertical line touch my graph in only one place? So no matter where you put this vertical line, it should only touch your graph in just one place. And if it does, like this one does, this was our example point here, it only touches the graph in that one point. So that would pass the vertical line test, which means it is a function. Now, for contrast, if we look at graph B, as I sweep this across, and let's take this point as our example, this vertical line touches our graph in two different places. So for that x value, we have two different y values, and that makes it not a function. So vertical line test, sweep it through, it should only touch your graph in only one place, no matter where you put that vertical line. All right, let's look at minimum and maximums. Now there are two ideas for minimum and maximum. One would be the absolute minimum or absolute maximum. That is just simply the highest y value is going to be for your interval is going to be your absolute maximum, and the lowest y value for your interval will be your absolute minimum. But for a relative minimum and a relative maximum, which is also known as a local minimum or maximum, they give you the official definition, and I'll let you read through those. But a good way to think of this is for a relative or local minimum or maximum, you should be able to put an interval around that point, and within the interval, within that local neighborhood, it is the lowest point if it's a minima, relative minima, or the highest point if it's a relative maxima within that interval. So that's why here we're looking at intervals. So if you can put an interval around the point and it's the lowest or highest point in that interval, then that's what makes it a relative or local minima or maxima. And we're actually going to use the graphing utility to find these. So they want us to find the relative minimum and relative maximum of the function given by this equation. So if we look at our calculator, let's pull the calculator up. Again, we're using the TI-84. And first thing you should always do when you get your calculator and turn it on is check your mode, make sure your mode is correct. And for this, we want to have everything on the left checked. So we want to be in function mode and everything checked on the left, except for clock. Don't worry about clock. So the mode looks correct. So we're going to go right into y equals, and we're going to put this equation in. So it's negative, remember negative not minus, it's negative x to the third power, and then plus x. So negative x cubed plus x. Let's do a standard window. So we're going to do zoom standard, which is zoom 6. That gives us the window from negative 10 to positive 10, negative 10 to positive 10. All right, so we can see there's some stuff happening on our graph near the origin. So let's zoom in a little bit. And I'm actually going to do it manually because I want this to look realistic. So I'm going to try to put it in that 3:2 ratio. So if I go to window, instead of negative 10 to 10, let me do negative 3, enter, to 3, enter. So my x is negative 3 to 3. And then if my y's are negative 2 to 2, then I know I'm in that 3:2 ratio. You could do 6 to 4, you could do 9 to 6, anything that puts you in that 3:2 ratio. And I would leave the scales for x and y at 1. All right, so now if we go back to our graph, we'll see, all right, now we see a little better graph. That's our cubic function. So it looks like this will be a minimum and this will be a maximum, but we need to find out what those points actually are. So to do that, on the graphing calculator, we go to second trace. Notice how it says calc above. That's the calculate menu. Since it's in blue, that means we hit the blue button first. So it's second trace, gives me the calculate menu. And let's do the maximum first. We're going to choose maximum, which is number 4. I can either arrow down and then hit enter, or I can just hit the number 4, either way. Now it's going to ask me for a left bound and a right bound. So we're going to create an interval that is going to capture that maximum. but we want to create an interval that's not too big where it captures another relative minimum or maximum. We want to capture just the top of the hill. As you can see here, local maximums would be on the top of the hills, and local minimums would be on the bottom of the valleys. So a good interval that definitely captures that, I'm going to say from 0 to 1 will definitely capture that. So left bound, I'm going to say 0, enter. Now I want to right bound, I'm going to hit 1, enter. And then it's going to ask for a guess. First of all, notice how it does give a little feedback to show you where your interval is, and yes, it does capture that maximum. Now the guess, this goes back to when calculators were not very powerful. So it would take the algorithms a while to run. So if you could give it a guess that's close to the answer, then it could find the answer a little quicker. However, nowadays these calculators are so fast, the guess really doesn't matter. So just go ahead and hit enter for guess. It doesn't matter. And then it'll find the maximum there's your x value, there's your y value of your maximum. And you would write that down to be one of your answers. That is your relative or local maximum. And now for the minimum, we're going to go, we still have a graph in there, so we're going to go back to second trace, which is the calculate menu. This time we want number 3, which is the minimum. And we want a left and right bound that's going to capture the low point there. So I'm going to go from -1 to 0. So left bound, -1. Remember, negative, not minus. So -1, enter. Right bound, I'm going to go with 0, enter. Guess doesn't matter. We can get our little visual feedback, make sure we're capturing that minimum. So guess doesn't matter. I'm just going to hit enter. And there is our minimum. So we can find the minimum, we can find the maximum. And just as a quick little recap, after we check our mode, of course, we go into y equals and put the function in. Then we go to the window, and I chose -3 to 3, -2 to 2. That keeps it in a nice realistic setting because it's that 3 to 2 aspect ratio. And then we go to second calculate. For the maximum, we use the interval from 0 to 1, and this was our maximum. For the minimum, we use the interval from -1 to 0, and this was our minimum. Okay, let's talk about piecewise functions. So if we look at graphing a piecewise function, piecewise functions are ones that have more than one rule for the function depending on the value of x. So depending on which interval our input lies in, that'll give you a different rule. Now if you notice, both of these are linear equations because they are a first degree polynomial. So the graphs of both of these parts are going to be lines. So this piecewise function is going to be 2 lines, basically. Now the lines are not going to go forever to the left and forever to the right. They have an endpoint. And 1 is that critical value, that upper and lower bound of these 2 lines. So if we look at the first one, this is going to be whenever x is less than or equal to 1. So whenever x is to the left of 1, at 1 or to the left of 1. So we're going to start with the critical value, and if x is 1, then it would satisfy this interval, which means we use this rule. So 2 times 1 is 2, plus 3 is 5. So if x is 1, then y is 5. That is going to be a point on the graph. And then as I go to the left, because this is less than, as I go to the left, I will continue this line, which happens to be in y equals mx plus b format, which means the 2 is my slope. Now I can use that slope to go up 2 over 1 to find another point, or I could go down 2 left 1, which is the way I want to go because I want to go to the left. So down 2 left 1, that gives me a second point. Once you have 2 points, you just connect the dots and you have a line. So this would be our line going in this direction. It would actually be a ray because it has an endpoint and goes off into one direction. And now that does continue on forever, any values where x is less than 1. Now to the right, we're going to start again at 1. We're starting at 1, but it's not going to be included in the interval. So if if x is 1 and we put 1 into this rule, this equation, then it'll be -1 plus 4 is a +3, so 1, 3 would be a point on here, but it's not included in the interval, so we're going to do an open circle. And then the graph is going to exist to the right of 1, because greater than means to the right. And then, again, y equals mx plus b format means our -1 is our slope. So I'm going to go down 1, right 1 to give me a second point. And connect the dots, go off in that direction with our line, and that would be the entire graph. That would be the graph of the piecewise function. Notice how when x is 1, it's not actually included in this part of the graph, it's included in this part of the graph, because that's the one that has the or equal to. Alright, the last thing we're going to look at is even and odd functions. And we're going to start out with the geometric interpretation and then go to the algebraic interpretation. So geometrically, an even function, and here's the rule algebraically, but geometrically, it's going to be symmetric for an even function, symmetric with respect to the y-axis. That means it's going to have left-right symmetry with regard to this y-axis. So you can think of taking this branch, and if you rotate it over the y-axis, thinking of it three-dimensionally coming out from the screen and rotating across, then this point, as you rotate across, becomes this point, and this branch becomes this branch. Or more specifically, is another way to look at it, if you take any point on the graph, then you take the distance to the y-axis, and in geometry, distance means perpendicular distance. So if you take any point and drop a perpendicular to the y-axis, because that's what we're symmetric with respect to, if you drop a perpendicular to the y-axis, then you would take this segment and continue it that same distance through the axis, and you're going to arrive at its corresponding point. This is the left-right symmetry that we're talking about, which makes it an even function. Now, if it has I'm going to skip the middle one for a second. If it has up and down symmetry, this one has left-right symmetry. If it has up-down symmetry, in other words, this segment, if you continue it through to down here, this has up and down symmetry. So this is symmetric with respect to the x-axis. However, this would not be a function because it would fail the vertical line test. So left-right symmetry is a function. Up and down symmetry is not a function. So this is simply neither even nor odd because it's not a function to begin with. Now an odd function has symmetry with respect to the origin, which means one of two things. Here, if we flipped this across the y-axis, then we got the same branch, basically. If we took the branch to the right of the y-axis and flipped it over, we get the branch to the left of the x-axis. And over here, if you take the up and down symmetry, if you take this branch and flip it over the x-axis, you would get this branch. Well, here, it does fit the flipping pattern, but you would do both of them. If I take this branch and reflect it across the y-axis, I would have a branch that looks like this. And then you take that and flip it over the x-axis, I would have a branch that looks like this. So you could flip it horizontally and then vertically, or you could flip this vertically to make this branch, and then horizontally to make this branch. Either way it would work. But you're flipping both horizontally and vertically. Now, another way to look at this, a second way to look at this, is you take any point that's on the graph, and just like here, we found the distance to the y-axis. Well, here we would take the distance to the origin, which would be a straight line distance. So from any point on the graph, you take a segment to the origin, and then continue that in the same direction for the same amount of distance, and that will give you its corresponding point. So that would be symmetry with respect to the origin. That's why it's called with respect to the origin. And this one was called symmetry with respect to the y-axis. Alright, so that would be a geometric way to find if it's even, odd, or neither. Now let's look at an algebraic way. And we're going to take these three cases here. So when finding algebraically whether something has symmetry with respect to the xy or neither, or whether it's an even, odd, or neither for its functions, our first step is to replace x with negative x. And then we are going to simplify. So starting with a, we have g of x equals x cubed minus x. So I'm just going to copy down the actual equation. Wherever I have x, I'm going to replace it with a negative x, and following good habits, we're always going to use the parentheses when we replace. So x becomes negative x becomes negative x. And then we simplify. We try to get rid of double negatives, for example. So here we have negative x quantity cubed means negative x times negative x times negative x, and 3 negatives is a negative. So we have negative x cubed, and then here a negative of a negative times a negative is a positive, or in other words, 2 negatives is a positive. An even number of negatives is always going to be positive, and an odd number of negatives will always be negative. So after I simplify, I get this, and the first thing we do is compare it to our original function. And here it is not equal to our original function. If it is equal to the original function, then it will be even. However, it's not equal to the original function, therefore it is not even. So our next step is to factor out a negative sign. And if I factor out a negative, I pull a negative out, that creates a parenthesis, and it'll change the sign of each of these. So it becomes a positive x cubed and a minus x. Now, if what I have inside is the same as the original function, which it is, then that means when I replace x with negative x, I get the negative of f of x, which was the rule for an odd function. So notice how this is equal to the negative of f of x. Therefore, and the 3 dots is the symbol for therefore. Therefore, this is an odd function. Now, let's look at b. We have h of x equals x squared plus 1. So b equals x squared plus 1. I replace x with negative x everywhere that it appears. It only appears once, though. So this gives me negative x quantity squared plus 1. Now I'm going to simplify. When I simplify, 2 negatives is a positive. And notice what I have is exactly what I started with. So replacing x with negative x results in the same thing I had to begin with, which was the f of x. Therefore, it is an even function. So if you replace x with negative x and you get the same thing, you have an even function. If you get the negative of what you started with, you have an odd function. If you don't get either of those two, you would have neither. Let's take a look at that example. So if we look at C, we have f of x equals x cubed minus 1. That's our equation, or our expression. And here I'm first going to replace x with negative x. That gives me negative x quantity cubed minus 1. Then I simplify. So 3 negatives is a negative, which gives me this expression. Now this expression is not equal to what we started with, so it's not equal to f of x. And to find out if it's equal to the negative of f of x, I would factor out a negative sign. When I do that, I get a positive x cubed and a positive 1. And notice how that inside is still not equal to what we started with, so it's not equal to negative of f of x. So if it's not equal to either of those, then we would say, therefore, it is neither an even function nor an odd function. So functions can be even, functions can be odd, or they can be neither. Okay, and that would be the algebraic approach for even and odd functions. And we're done.